Welcome. Today, we're diving into how queuing theory applies to Apache Kafka. If you've ever wondered how messages flow through Kafka and what happens when things get backed up, you're in the right place. We'll break down Kafka's core components, see how throughput is calculated, and understand why consumer lag can occur. By the end, you'll have a clear picture of how Kafka handles high message volumes and what you can do to optimize your system. Let's start with the basics. A Kafka system is made up of three main components: the producer, the broker, and the consumer. The producer is responsible for sending messages into Kafka. The broker acts as the storage unit, holding on to those messages until they're needed. Finally, the consumer reads and processes the messages. Each part plays a critical role in ensuring data flows smoothly through the system. Imagine an e-commerce application. Whenever a customer places an order, the producer sends an order-placed message to Kafka. The broker stores this message until a consumer is ready to process it. This setup ensures that no order is lost, even if the consumer is temporarily busy. It's a reliable way to handle high volumes of transactions, especially during peak shopping times. Let's talk numbers. Suppose processing a single message takes 10 milliseconds. That means in 1 second, a single consumer can process 100 messages. This calculation is straightforward. 1,000 milliseconds divided by 10 milliseconds per message equals 100 messages per second. Understanding this rate is crucial for planning your Kafka deployment and ensuring you have enough consumers to handle your workload. Here's an important detail. Kafka consumers are not thread safe. Each consumer maintains its own internal state, such as offsets and partition assignments. If multiple threads try to use the same consumer, they could interfere with each other, leading to inconsistent state or incorrect offset commits. That's why in Kafka, one consumer always runs on a single thread to avoid these issues. To increase throughput, frameworks like Spring Boot use concurrency. By configuring a higher concurrency value, Spring Boot can create multiple consumer threads, each with its own Kafka consumer. For example, setting concurrency to 4 means you'll have 4 consumer threads and 4 Kafka consumers, all working in parallel to process messages faster. Let's do the math. If each consumer processes 100 messages per second and you have 4 consumers, together they can handle 400 messages per second. This linear scaling works as long as there are enough partitions and resources. It's a simple yet powerful way to boost your Kafka system's capacity. Now, imagine you deploy your application on 5 servers, each with a concurrency of 4. That gives you a total of 20 consumers across your system. This setup can dramatically increase your processing power, but there's an important caveat to keep in mind. Kafka assigns each partition to only one consumer within a consumer group. If your topic has just 10 partitions, only 10 consumers can actively process messages at any time. The remaining 10 consumers will stay idle, waiting for their turn. This means adding more consumers doesn't always lead to higher throughput unless you also increase the number of partitions. In our example, with 20 consumers but only 10 partitions, only 10 consumers are actively processing messages. The other 10 are idle, essentially waiting for their chance to work. This is a common scenario in Kafka deployments and highlights the importance of aligning your consumer count with the number of partitions. Let's look at message rates. Suppose your producers are sending 5,000 messages per second, but your active consumers can only process 4,000 messages per second. This mismatch creates a backlog of unprocessed messages, which can grow quickly if not addressed. The difference between messages produced and messages consumed is called consumer lag. In our example, there's a lag of 1,000 messages per second. These unprocessed messages remain in Kafka, waiting for consumers to catch up. Over time, this lag can grow, potentially leading to delays or even data loss if not managed properly. Picture a growing queue of messages inside Kafka. As more messages are produced than consumed, this queue gets longer and longer. Monitoring consumer lag is essential for maintaining system health and ensuring timely processing of all messages. To optimize Kafka throughput, you need to balance the number of partitions, consumers, and the rate at which messages are produced. Increasing partitions allows more consumers to work in parallel, reducing lag and improving overall performance. Regularly review your configuration to ensure it matches your workload. In summary, understanding queuing theory in Kafka helps you design systems that can handle high message volumes efficiently. Remember to align your consumer count with partitions, monitor consumer lag, and adjust your configuration as needed. With these strategies, you'll keep your Kafka pipelines running smoothly and avoid costly backlogs.